kind of review, what we're trying to get is that rate equals our rate constant times the concentration of CH3, 3CBr times the concentration of hydroxide. We do not know the orders. We'll call them X and Y. So what we want to do is go to the experimental data and say, what can the experimental data give us that would allow me to determine X and Y? Do you have ideas on where to go with that? Or should I give you some more mathematical support? I know it's 8:30. You guys ready to talk it out, try and figure it out? Sure. Okay. Talk to your group. So we're going to go ahead and get started and talk through some of this. Some of the math that kind of supports this, which is what I was kind of asking about, sounds like based off of hearing a few things floating around, they go, oh, well, the slow step. A slow step is a mechanism. There is no mechanism up here. You can't look at a slow step because there isn't one. What you can look at is the individual experiments. And so the idea is that you would compare experiment 1 to experiment 2, or experiment 1 to experiment 3, or experiment 2 to 3. And you're making that comparison very selectively. Okay, so a couple people sounded like they knew what they were doing behind it. Okay, so if you think you're one of those people, what 2 experiments do you think you would compare?
1 and 2 for CH3 for the first and second for OH.
Okay, cool. That's all I need is 1. So we want to compare 2 experiments. Let's compare experiment 1 and 2. Green reaction and orange reaction. So what we could do is take our rate and we could plug it into the rate law for the green reaction. So we'd be using green concentrations and green hydroxide. Kind of, sort of. The rate constant is a constant, but I don't know what the value is. X is also a constant, but I don't know what the value is. Y is a constant, I don't know what the value is. So to go through and solve that, that is, said in fancy terms, impossible. Okay, I can't do that. But I can also look at the orange reaction, okay, experiment 2, and I can set up the same thing. And you go, well, it's going to be the same problems. Except within these 2 experiments, I now have a useful bit of information. I know the rate constant is the same for both those reactions. Theoretically, we go through, well, isn't the exponent the same too? Yeah, that's more complicated math than I want to deal with. So what we can do is determine what the concentration or what our rate constant would be. So the rate constant green will equal rate over the concentration of those 2 things. Yeah? To those orders. Do the same thing with the orange, rate to those orders. Okay? So far make sense? Okay? Now what we're going to do is group like terms. Okay? Because I'm definitely out of space. I'm going to erase those simplifications above. Is that okay? Mm-hmm. I can always bring it back if need be. And I'm going to get a new expression. I'm going to get my green rate over my orange rate. This will then equal my green concentrations over my orange concentrations. Everybody okay with that? Why is that valuable to me? Well, this goes back to your selection and yours as well. Okay, you said, I want to look at experiment 1 and 2. Okay, well, if I look at experiment 1 and 2, what happens to the concentration of hydroxide? It stays the same, which means when I go back to this expression that I just arranged, what happens to that term? It entirely cancels out of the expression. Why is that now powerful for me? Well, if that cancels out, and I look at that expression, do I know the rate? Yeah, that's from my experimental data. Do I know my concentrations? Yeah, that's from the experimental data. So the only thing left is the order with respect to our carbon-bromine compound. Okay? Mathematically, we can do a bunch of and I have to erase all that stuff now too. We could do a bunch of goofy mathematics if we really wanted to, but I have a feeling that if you talked to those people that were going through and running their calculations, they didn't look at any goofy mathematics, they just kind of did it in their head. For those people that pulled that off, is that true? How do you solve for the exponent? Well, you could plug in values and see what happens. Okay? And I probably plugged them in backwards. I did. Oh well. Okay? So 0.011 is our rate for our green. Rate for the orange was 0.022. What does that equal? 1/2. Bromine. 0.05 over 0.1. What does that equal? What does X have to be? It has to be 1. Mathematically, it comes out of that. Okay? I'm saying a little quizzical face because I'm betting you went through and said, but it doubled. It's all a matter of perspective on which direction you're looking within that system. Okay? Most people struggle with fractions. I conveniently picked the wrong alignment of those things to get the fraction where we see the doubling. Okay? But it's the exact same protocol. It's the exact same mathematics. Okay? Could you actually legit solve for X? Yeah, do some, natural log stuff, and you could actually solve for it if you really want to. Or we realize, what are our possible values for our X?
What if it's easier for us to do log?
If it's easier for you to do log, go ahead. Okay? Said another way, 1/2 to the X power. It's easier for you to go through and do the log instead of just saying X is 1.
Yeah.
Okay, that's fine. There are 3 possible values for X. What are the 3 values? 3 doesn't work. Go back to our graphic examples. 0, 1, and 2. That's it. Those are your only values. Right? So you could just plug and chug in here. When might you need to use all the natural logs? If you picked a bad sequence of experiments, okay, you could potentially be forced into using natural logs. Okay? In my experience and expectations of what I've seen from your class, that's not going to happen. What you're going to get are simple patterns where they come out as clean ratios all the way through. Make sense? So, long mathematics, whoops. I'm going to leave that there for the moment, I think. Long mathematics told us, when I compare experiment 1 to 2, that X equaled 1. What other experiments could I compare? Because I don't know Y yet.
2, 8, 5, 3.
I could compare experiments 1 and 3. I can go through all the mathematics. Or what I can go through and do is look at why would I pick experiment 1 and 3. 1 and 3, what happens to the concentration of the CH3CBr? Remains the same, which means it has no effect on the rate. What happens to the concentration of hydroxide? It doubled. What happened to the rate? It stayed the same. Did the hydroxide have any effect on the rate? And if it doesn't have any effect on the rate, what must the order be? 0 order. Okay? And if you don't like that kind of thought process behind what's happening in the chemical concept, you can plug in the mathematics and do the substitutions. You'll note the concentration of bromide would cancel, and what you'd be left with is a similar expression, except you'd be looking at hydroxide over hydroxide. Exact same mathematical system. Kind of, sort of? So what does that mean for us? So all of that stuff put together means we can go back to our rate law that we wrote up there, and we can say our rate law is actually rate equals K times the concentration of CH3,3CBr, and that's it. We can imply the 1. Or you can show it. It's up to you. If you've got a lot of mathematical experience, you might be like, well, I don't want to show a 1 because it looks ugly. That's fine. If you're like, I need to see the 1 so I know it is first order, then by all means, show a 1. It's entirely up to you. Why am I not showing the hydroxide? It was to the 0 order. I could put it in there, but then I could also put in pineapples. Should I draw pineapples to the 0 order? Maybe tables. Right? They're irrelevant to the overall system, so I can drop them from the mathematical expression. I don't have to worry about it. And that now becomes the rate for my reaction. That's kind of wicked. The experimental information gives us that rate. Okay, so what we've now done is looked at determining a rate law for an overall reaction 2 ways. We looked at mechanisms. Oh, slow step. Yes. Awesome. Okay, that information was given to you. Now we've looked at experimental data. Both of them get to a rate law. What's the next natural confluence of events? We delete everything. And we bring them together. So from the previous slide, we know that our rate law is as established up here. Experimental evidence tells us this. If we look at just the Lewis structures of what's happening within this reaction, hopefully you all accept this as a mild shorthand. What happened? Can I get away with this? Fine, I'll just draw it again. Whoops. We're doing this based off of the information given to us in the equation, right? We've added a little bit more information because we've drawn it out as a reaction, where we can see the lines and the bonds and see what happens. What changed as we went from our reactants to our products? You're talking to yourself. Be louder. They swapped. How did they swap? What had to happen for them to swap?
Carbon-bromine bond was broken.
This bond was broken. What else happened? That one had to be broken off, and if they swapped, what did the hydroxide have to do? This bond was formed. That's it. You can look at how the electrons move. Wrong class, that's OChem. Don't stress about it now. Okay? Arguably what we're looking at here is OChem. And so what someone went through and did is looked at that overall reaction and said, well, how could that possibly happen? So their brain thought a mechanism. They said, both those things happen at the exact same instant. Which means one step. Or we break the bond first, then we make it. 2-step. So these mechanisms, I didn't spell Brian, right? A brain thought. Right? Are you responsible for the brain thought? To my understanding, not at all. That's OChem. In this particular case, it's legit OChem. Okay? What you're responsible for is, given these mechanisms, which one of them matches the experimental evidence? But I don't know how to do it. You do. The experimental evidence gave us the rate law in the box. Prior to doing the experimental evidence, did we determine rate laws for mechanisms? Yeah, we did. So what we could go through and do for each of these reactions or these mechanisms is say, what would the rate law be? Because these are now elementary mechanistic steps. What's the rate law for that top experiment? Starts with kind of accept K. I would say rate first, but K makes sense. K times the concentration of the reactants. CH3,3CBr and hydroxide. Why and hydroxide? It's a reactant. We go to mechanism 2. Which of those steps do we care about? Why the first one? That's the slow step. So I would write out the rate, and I would get rate equals K times concentration of the reactant. What's the reactant? Are there any other reactants in that step? No. Which means, what's the rate law for mechanism 2? It's in red. It's done. Which of those two mechanisms matches the experimental data? Mechanism 2. So what do we say about mechanism 1? Or whoever came up with mechanism 1? Near, you're an idiot, you're wrong. Right? And it's mechanism 2. In this particular case, depends on other things, and both mechanisms can be valid, depending on those circumstances. But those circumstances have to change. How would we know the circumstances change? Experimental data. Without the experimental data, you cannot confirm a mechanism. You can just say, this is what would dictate how fast it would go. But that's it. Kind of makes sense? Once we know what the rate law is, what else could we do? Next slide. What's the value of the rate constant? How do I solve for the value of the rate constant? Do I know the rate? Yeah, it's in the experiment. Do I know the concentration of the CH3CBr? It's killing me to say that, by the way. Yeah, so what can I do? Plug it in and solve for K. For which experiment? It doesn't matter which experiment, because it's called a rate constant. It doesn't matter which experiment I play with, it's always going to give me that same rate constant. Right? Within a little bit of gray area. Right? Why would there be any variability?
Plug in the wrong initial rate or the wrong voltage.
No, that's you screwing up. That doesn't count for variability. Do all experiments produce perfect data? No. The real world produces slightly variable data. So how would we get a more reliable rate constant than looking at a single experiment? Do it multiple times, and then what? Average. Right? Once you have that average, you now have a reliable rate constant. How do you know what the variance is? We'll run a whole bunch of experiments and test it out. Okay? Are you going to be expected to run any of those experiments? For a lecture? No. You're given the data, you just deal with what you've got. Right? Should you go through and calculate the rate constant for all 3 experiments and then average them on an exam? Or on you get called quizzes.
Can you?
I don't know. Do you have time? If you have time, sure, why not? It proves you know that further step. Don't have time? Do it once. Say this is what it is, and move on. Kind of make sense? Okay. Questions? Feeling a little better about it? Okay. I'm not 100%, but I did review the practice quiz questions. I would argue we've covered them now. Right? There's a little bit of nuance, but I think the content is pretty much there for the practice quiz. Okay. So we're now to where we should be, which is good. It's not too bad. Active, sorry, I didn't update this. I got the date, but I didn't fix anything else. Active, or not active, Alex, homework number 2 would be due this week. Okay, so you should be working on getting that done. And there is no written homework as far as I've seen. Your Unit 1 quiz, from what I have seen from the syllabus, okay, because it took me a little while to find it, your Unit 1 quiz is not this week, it's next week, which I think was your question. Okay, so allegedly next Wednesday, you have your Unit 1 quiz. I don't know anything about the logistics behind that. I'm just doing what I'm told. That's something, a conversation I need to have with Dr. Schnipp. Okay? My understanding is the practice quiz does a really good job of keeping you in alignment with what's on that quiz. So if you've not had our classes before, you should review the practice quiz and make sure you're good to go on that. Okay? Notes, I will say, it sounds like our policy has changed since last spring. You only get one sheet of notes.
It is back and forth, right?
What's back and forth?
Like both pages, both sides, on that.
As far as I know.
Okay.
That's what I will run until told otherwise. How about that? Okay? And then we can do retakes. We'll address retakes when we get there. Okay? That'll be fun to logisticize. So, what do we have here? Another practice problem. Hooray! Take a swing. See what you guys can come up with. Should we time you? I'll time you so you get an idea. I talked through that and recorded it. Apologies. So experiment 2 and 3 didn't change, so I crossed it out. I'm looking at hydroxide. What happened to hydroxide? It increased by 3. What happened to my rate? It increased by a little over 3, I think. I didn't have a calculator, but that looks ballpark 3-ish. Right? So again, it's 3 to the equals 3x. That's a first order reaction. That gives me my rate expression. Okay? I balked at solving the rate constant. I was like, there's no way I'm going to be able to solve with that. I can't do that math in my head. And so I jumped to the next question, which was a second order reaction. How do we determine the order of the reaction? The order of the reaction is the sum of the superscripts. It's the sum of the individual orders. That's how we get the order for the reaction. And then, to be honest, I remembered what the answer was for the rate constant last week. So I was like, that number wasn't too bad. Maybe I could actually solve for it. I don't remember which experiment I grabbed, but our rate constant is equal to rate over the concentrations. Grabbed an experiment, 0.041, divided by the two concentrations, 0.1 and 0.1. 0.1 is really just 10 to the minus 1, which means I can pull it up as a superscript and just do 10. That's a shift to the decimal twice, and I get 4.1 ballpark as my rate constant. If you went through and used a different experiment, what you will find is your rate constant was not exactly 4.1. I believe all of them come out to 4 something. I want to say there's a 4.3 ringing around in my head. Whether that's true or not, I don't remember. Okay? But they're all 4 something. That's pretty close. Deciding whether it's close enough or not, I would argue, is going to be how much time do you got. If you got time, you double check everything and see how it runs. If it comes out the same, it comes out the same. That's what it was. Does that make sense? You can kind of track the work. Do you have a question?
Oh, no,
No?
I did.
Okay. Kind of get a feel for that process. Okay, which takes us back to the slides. So what we would go through and do, we've got our rate law and the rate constant. What does this tell us about the mechanism of the reaction? That's a little bit of a harder question, but we've got some ideas on what the orders could be and what their plausible mechanisms are. That was earlier slides. Should I go back and pull those slides up so you know what we're talking about? Going once, twice. There was a couple head shakes, yes. If you get sick of scrolling, stop looking. Whoop. That was these things. First order reaction, one molecule reacts without a collision. They pull apart. Right. Second order reaction, 2 molecules of the same substance collide. Okay, and react. I don't remember if it was this class or a different one. Right? One of the things that's misleading potentially within this image is you think, oh, 2 things come together and they produce 1. Not necessarily. Okay? When we're talking about these mechanisms, what part of the reaction do we care about? That's a hard question. Mechanisms are all about what? I am speed. And if we're talking about speed, the only thing we care about is the reactants. Okay? This particular second order reaction is showing a product where they fully combined. Maybe they could have combined and ejected a piece. That would still be a second order reaction because it was two pieces involved in making it. Okay, so don't put weight on the product side, put weight on the reactant side. Does that make sense? Okay. Our other potential second order reaction is where they were two different things. Is it not? Oh, because I'm in my thing. Two different particles. So this okay, here we're about to scroll again. Don't look. So that last question, that last question is asking us to think back to those general diagrams and say, could we make an assumption about the mechanism? We could. It doesn't necessarily mean we're right. Okay? But it gives us some information that we could potentially guess that those two particles must collide. Kind of make sense? Mm-hmm. That would at least be consistent with our overall rate law. Okay. Another one, summarize by filling in the table. This is again for you guys to think about, process, talk through at your table. I'll write in everything. So if you guys want to first talk about what you should be writing down for each of those, I think that makes a whole lot more sense than just trying to frantically figure out what the answers are. Remember, the lecture is recorded. You could always go back to a certain time. That answer, I'll say, for your notes is at 27:30. But that's not true. And I did say 30 officially. It's 30 is roughly when we'll talk through it. So we've got our rate laws. Hopefully everybody's nailed those. The rate constant units is almost always a sticking point, and that causes a lot of problems. Mostly because we ignore the unit when we talk about rate. What's our unit for rate? Concentration per second, concentration per time. Our concentration unit would be molarity. So if we're looking at each of those equations, for a zero order reaction, the rate is still molarity per second. If it only equals the rate constant, what must the units on the rate constant be? It has to be molarity per second. You don't get a choice because the units have to match. And if there's nothing else multiplied, you can't bring in another unit. Right? Which then introduces a potential another issue, is that when you look at capital M, or molarity per second, as I'm writing it, you won't see it written like that in a textbook. You'll almost always see it written like that. Why? They are exactly the same thing. Which one shows you a clear numerator and denominator? Red or black? Red. Which one's easier for you to manipulate, red or black? When dealing with units, there's a rare student that can deal with the black one. 9 times out of 10, even the student that says, oh, I can totally do the black one really well. You give them the red one, they do it faster and better, more accurately. Students usually struggle and fail with exponents, particularly negative exponents. Okay? So why the hell would we ever use a black unit system if the red one is far superior for our use in manipulations? How do we transfer knowledge from one place to another? Through the written word, and that written word comes to us from the computer, ultimately the typewriter. Is it easy to show fractions on a typewriter? No, it's virtually impossible. So they had to create a notation, a mathematical notation that would allow them to transfer that knowledge so that symbology could then be translated by whoever was reading it at the other end. Okay? That's why it exists. I think we should abolish it, because at this point, what can we do really well? We can write fractions on our computer very, very smoothly. We don't need to deal with this stupid inverse unit. Okay? What are we waiting for to adopt the new standard? Old people to die. Sorry. That's pretty brutally honest, but that's how it works. Okay? The people that grew up on that symbology are used to manipulating that symbology. That's the only language they're going to talk in. Okay? Which means you, as younger people, now have to learn both standards. And in 50 years, guess what's going to happen? Probably a new notation. Everybody's going to hope you die so they can move on to a new notation. Yay, welcome to science. Okay? So it's how you manipulate that language and understand it within it. You're responsible for being able to deal with all of those language systems. Which means we move to the next one, first order. What's our unit for rate constant? Molarity squared over S. What's the units for concentration? M. If I run the calculation as written, what would my rate unit be? M to the third power over S. Is that what my unit is for rate? Nope. So is it M squared? Nope. What is it? It's per second. The rate constant unit changed. It just switches to per second. There's no molarity. Why not? There's no canceling here. Molarity times per second will equal molarity per second. There's no need to bring in a molarity. Where's the canceling going to happen? And our last one, that's when we have to have a cancellation happen. Okay. Again, fractions people tend to dislike, particularly in computer systems. So you would see capital M S minus 1. Make sense? All right, that last one, second order, I want to talk about that real quickly. If we're looking at a second order rate law, this top one, is that a valid second order rate law? 100% valid. That is perfectly acceptable as a second order rate law. There should have been a little bit more context within this question to state what the reaction was. And the reaction that we're trying to talk about, as we erase more of that title, is A goes to B. And if we have the reaction A goes to B, does that top rate law make any sense? No. Now it's lost information. But you needed that key tip off of what's going on. Does that make sense? Okay. So I like that top one. It's a good thought. Unfortunately, it just doesn't fly for this particular question. Okay. What's happening with our plots? This is where if you're really good at, what's the thing with math? Geometry? Calculus? I don't know. With formulas? And plotting things? Sure, let's go with that. Okay. The top two are technically linear, but the top one is constant because there's no concentration, there's no other variable. Okay. First order, they're going to change with respect to each other. The last one is going to change as a squaring, which looks parabolic. Okay. When A doubles, what happens to the rate for the top one? What happens to the rate for zero order? Concentration doubles, the rate stays the same. Next one. When concentration doubles, the rate doubles. Last one. When the rate doubles, I keep saying that. When the concentration doubles, what happens to the rate? It squares. Okay, in this particular case, it quadruples. I don't know if that's spelled right. Okay. I would argue the squaring is probably a better system, 2 squared, so it's taking into consideration that order. Does that make sense? Okay, so if you wanted that table 3438, it's complete. Whoops, I was about to stop the video. So our rate constant units, okay, this is just going back to it because it, again, is a struggle to kind of deal with. If we just consider our units, the rate, see if I remember my coloring, my rate is always going to be molarity per second. Oh, I think this was the coloring I used. There, for the first one, our zero order, we have no other thing. We just have the rate constant, which means the rate constant must be units of molarity per second. We move to the other one. The one that we do know is our concentration has to come in as molarity. Okay? Technically molarity over 1, which means the rate constant has to come in as 1 over seconds. Make sense? Kind of the same deal for the last one, our molarity, but we have to take into consideration that it's squared. What does the rate constant have to be? It's always going to bring in the seconds in the denominator, but it's also going to have to bring in the molarity so we can cancel one of those squarings. So far, so good? I think I'll accept that as yes. Okay. So our graph options, we've got our 3 graphs. That's not 3 graphs, that's 4 graphs. Do you understand what's going on with the first 3? What's the second one? There we go. There were a lot of different answers that could have gone with it. I wanted to hear first order. First one? 0 order. Third one? Second order. Fourth one? What do we say about third order?
0.
Doesn't happen. This is an interesting one. Okay? This isn't matching any of our other systems, so let's walk through what's happening. As we increase the concentration of our reactant, eventually what happens to the speed of our reaction?
It becomes like constant.
It starts to become constant. Okay? When could that possibly happen? What do catalysts do? All right, go ahead. Do you want to?
I was going to suggest the entire rate is second order, but concentration is first.
So you could start to look at breaking that down into 2 components. Yep, that's a neat idea. So initially, your rate is first order, and then it starts to become 0 order. What do catalysts do?
And they speed up the reaction.
They speed up the reaction by effectively changing how the reaction works. They grab reactants. If we look at an enzyme, okay, biologically it grabs an enzyme and it forces the chemical reaction to happen. And it makes it happen really, really, really fast. As you increase the concentration of reactants, your enzyme can grab more reactants, right? Until eventually what happens? Kind of the right idea. We run out of enzyme. There's now so much reactant that the enzyme can't grab it because it's physically in the process of working through a chemical reaction. So you end up adding so much reactant that you have saturated your enzymatic process. And if it's saturated, what happens to the rate? It tails off. Okay? And that's ultimately what's happening in there. It's an example of a biochemical system where you're looking at biological enzymes processing a chemical reaction. Kind of neat. So, what is the rate constant? Okay. The rate constant tries to factor in all those intangibles. When we're thinking about our rate, again, generally, K times our concentration of our reactants to whatever order. Just put an X up there. We can monitor the concentration of our reactants. We can look and determine the order of the reaction. Okay, how important is that reactant to the overall process? Okay. But that tells us nothing about how the reactants collide. So we've done the example a whole bunch with the pen, right? Right? If my reaction is capping the pen, what things control that? Well, how many pens and caps are around? That would control it. Okay? If I have more of those, we increase the likelihood that they connect. Okay? But what else has to happen? Well, they have to collide. Okay? Yeah, that made sense. Okay? But what if they collide sideways? we don't get a chemical reaction. So there's an orientation factor that's contributed into this. That orientation factor is constant for an individual reaction. Oh, it's constant. Oh, rate constant. Guess what the rate constant has factored into it? Orientation. Okay? But we could fix the orientation and what happens? Oops, that might have been loud for the microphone. It still doesn't work. What else needs to happen? Enough energy. Okay? Enough energy to force the chemical reaction to happen. Okay? So that rate constant takes those things that should be relatively consistent and constant for an individual reaction and just says, whoop, one constant. But could we start to pull some of that information out? Right? Like quantifying the orientation is going to become a bit challenging. But can you quantify the energy of a chemical reaction?
Yeah.
Okay. So how could we start to needle and pull that information out? Where we could monitor that is with our temperatures. Okay. As we change the temperature, do we change the speed at which our chemical reaction happens?
Mm-hmm.
Yeah, significantly. Okay. And temperature's a way to look at the total energy for our system. Okay. Or our average energy, not our total energy. So K has some information kind of stashed within it, and we want to try and be able to pull that out. Before we pull that out, remember this diagram? We talked about the fraction of molecules and kinetic energy, and it was blank, and I was like, I have no idea how to draw this except that I know the answer. Okay? What we're looking at is our distribution again. They smoothed it out, but effectively this is a histogram. Okay? There's an energy value and the number of particles that correspond to that energy value. And if we look at it over enough of a spread, we would see a curve like this. Okay? Regardless of the temperature, we will always have particles that have low kinetic energy, effectively zero. A collision happens, it gets pinned to the wall, things like that. They're going to stop it from moving. Okay? So that's always going to be there. As we slowly increase or look at our kinetic energy, we're going to start to see it increase, and then it's going to start to tail off again. Okay? And if we look at a chemical reaction has an activation energy. Okay? That activation energy we could put on this plot. Yes, that says kinetic energy, but what we're saying is what's the necessary kinetic energy for a chemical reaction to happen? So we could draw a line. Boop. You're like, well, why'd you pick that spot? I just picked it randomly. We just said for this reaction, it had kinetic energy at that spot. If we look at the success of making products, the only particles that can make products are the area underneath that curve. Yay, calculus. What happens to the curve when we increase the temperature? Okay. What do you mean it shifts? Do I just take the whole curve and slide it? No, because we still have to have that 0 point. So effectively what I would argue is less of a shift and more of a squish. I take that top and I push down on the bottom. That's going to start to push things out to the sides. Okay? Effectively it really only pushes one direction, so it's still not a squish. Okay? But you could start to see something like that. I drew it pretty awfully. Okay? Now when we run that chemical reaction, area underneath the curve, there's significantly more particles that can now make that product, that can transition from reactant to product. Okay? Kind of makes sense? Okay? Shown more beautifully, ta-da! More particles have achieved that energy and are now able to react. Okay? Is this something we see every day? Well, if you cook, yeah. Okay? What we're doing is increasing the energy to speed that chemical reaction along to produce something else. Okay? You can go to In-N-Out Burger and you can get animal style. What's animal style? I might be wrong. I think I'm right.
It's got it's grilled in mustard, it's got the spread, and it's got grilled onions.
Grilled onions. Why do we want grilled onions?
Tastes better.
It tastes good. It tastes better. Why is it tasting better? You've caramelized the sugars in it, which is a fancy way of saying you slowly burned them. Okay? And that creates a caramelization behind it that tastes better than raw onion. That's a combustion process. It's naturally happening. But we don't want to sit there and wait for our onions. We just order it regular and just be like, turn animal. You're going to be staring at it. It's going to disappear before then. Okay? Hopefully it molds and gets destroyed before those onions caramelize. So we speed that up with a little bit of heat. Okay? So, calculating our rate constant. We get this special equation known as the Arrhenius equation. Okay? The Arrhenius equation, we'll look at kind of where this came from, but it ultimately said, okay, how can we look at different measurements for a chemical reaction and see what causes it to change? Okay? And we talk about see what causes it to change. We know temperature affects the rate of our reaction. Activation energy is the energy up to the transition state. So we go, oh, we could measure that, except can we get the transition state? Does that exist? The transition state is a transition point. It's moving from one space to another. It never actually exists. And if it never exists, I can't measure the distance. So the activation energy, I can't explicitly measure. Okay? But I can measure the temperature, and I know the temperature is going to affect that system. Okay? What about the rate constant? Can I determine the rate constant? Yeah, that was all the experimental stuff we just went through and did. So I could go through and I could determine the rate constant, all those calculations we did, except in those calculations I add an extra variable. In all those other systems, did we talk about temperature at all? We didn't. So we can do those experiments again, but now change the temperature. And if we change the temperature, what's going to happen to the rate constant? It's also going to change. How much does it change by? How good are you at exponential functions? Okay? And really, you're panicking about exponential functions. Don't panic too much yet. Okay? Yet, yes. Okay? Because most scientists are not particularly good with exponential functions either. So we try to design experiments that would allow us to see them in linear relationships. Okay? So we've got some terms that we know that we need to kind of figure out or that come out of this. The rate constant, that comes from our experiment, so we can get that. Okay? T is temperature, which can come from an experiment. So that's cool. What other things do we see in there? I like your answer better than everybody else's. Our activation energy. Okay, EA. This is our activation energy. This would be neat if we could directly measure, but we can't directly measure it. We have to indirectly measuring it by looking at other things, like our rate constant and our temperature. So this is our activation energy. Then a couple people said A. I think we'll make you regret that now. What is A? Yeah, I kind of figured that would make. Okay. Oh, we've seen A's before. A's were concentrations of the reactant. How do we know they were concentrations of the reactant? 2-ish pieces of information we needed to see. One of those pieces of information we need to see, which is why you made a mistake, right? In determining your second order rate law. What did we need to see? We needed to see what the chemical reaction was so we could say it was A as the reactant. Okay? What else do we need to see to help tip us off that this is a chemical reactant?
The reaction.
You just said that.
Oh, sorry.
When we used A in all of our chemical reactions, what were its units? Molarity. How did we know they were molarity? There were brackets. Do we have brackets? No, this is not concentration. This is not the reactant. This is something else. One thing is it is a constant. This as a constant is gathering in all of those unmeasurables that we can't control. We still don't know about orientation. Okay? So as a constant, this just envelops the rest of the stuff that we don't have an ability to quantify, at least yet. Okay? So that as a constant is kind of our reaction. I don't want to call it a reaction constant because that gets dodgy with our rate constant. Okay? But we could bring in orientation. There's a big explicit factor behind that. What else is in there? R. What is R? Have you seen R before? Yes. Yes, you have.
Yeah.
Since you said R, you can't tell me what it is. What is R? The letter that comes after Q. Yeah? Okay. That was nonsense. That was the alphabet, for the record. I went high, so you didn't have to breathe that. Sorry. What was that? That's a hint. Why would I look at pressure? What does pressure measure? Not this. It's the gas constant. Okay? The gas constant, the good old 0.0821, right? People being like, is that the right? I don't remember. Okay, the more important part is what are the units on the gas constant? That one I do remember. Liters times atmosphere per mole times Kelvin. Okay? That should cause problems right away. Why does that cause problems? Say again? Yeah. If we're looking at this expression up here with our activation energy and our temperature, the activation energy is usually going to be in temperature of joules or kilojoules. Our temperature is usually going to be in units of Kelvin, so that one's okay. But are joules, kilojoules going to cancel with any of those units? No. So it is technically the gas constant, but these are units. And what can you do with units? You can change them. You can do a conversion to convert them into units that you do want. You could convert them into 8.3, I always get it confused with maybe I'm repeating pi, 8.314. Someone know the units? Dang it. Joules per mole times Kelvin. Right? You look that up. I'm not positive on that. Okay? So you could potentially have to deal with converting liter atmospheres into joules. Is that something you can do? Yeah, you probably don't want to. Okay? I don't think you'll have to, but that is something you'd have to worry about. And if that is units of joules and our activation energy is in units of kilojoules, what are we going to have to worry about? That we do the proper unit conversion. So you're going to have to make sure you track your units through the system to ensure that you're using the right units, the right numbers tied to those units to allow these calculations. What is the lowercase e?
It's a variable for like on calculation. What is it? It's exponential.
It's exponential. I don't know what that means other than it's the button on the calculator that you would press and it does the thing.
Yeah.
Okay? And as long as y'all are happy with that, I'm happy with that. Okay? What does this mean for us? So what we could go through and do is now run calculations. So the activation energy for a reaction is 56.8 kilojoules per mole. And the frequency factor, A, is 1.5 times 10 to the 11th per second. Or sorry, calculate the rate constant K at 298 Kelvin. So what are they telling you to do? Everybody's favorite. EA equals 56.8 kilojoules per mole. Our A is 1.5 times 10 to the 11th per second. T equals 298 Kelvin. Oh, and she conveniently didn't tell me what R was, so I look like an idiot. That's good. It's pretty normal. Joules per mole Kelvin. What are we supposed to do? We have to worry about the kilojoules to joule conversion and plug and shove. Shove the numbers in, punch it into the calculator, get out an answer. Ta-da, there would be your rate constant. So we have another way of solving for a rate constant. For those people that want to calculate that, go right ahead, that's okay. But I'm not stopping there. Okay? So we can use the Arrhenius equation to figure out our activation energy. Okay, so we can do it on the flip. Because remember, we can determine the rate constant through a series of experiments. We can also determine the temperature at which those rate constants were determined. We can then plot those. Temperature versus rate constant. Why would we plot them that way? Look at your expression. This is y equals e to the x. Okay? So all you're doing is effectively running that standard plot. Okay? And if we look at that line, is it a straight line? No. Okay, how do we know it's not a straight line? We can see it curve. But how do we know it's curving? We had to plug in our data. What if the experiment you ran was only those 3 data points? Would that look like a straight line?
Yeah.
Yeah. So that's where we have to be careful when we're running these experiments, is to run enough of a temperature range that we can see the curve on it. We could then tell mathematical computer modeling systems to go through and fit it to an exponential. Okay? But we don't have that. Yeah, we do. But we don't have that. So what do we do instead? We go back to our equation at the bottom, and I say, how do I rearrange that equation to give me y equals mx plus b? It's a good question. We'll talk about that on Wednesday.